Okay, so grade 11s, this is Ms. Stone, and as you know, I couldn't be here today in class, and I wanted to go through with you, though, an example of solving a similar scope of problem that you'll have to solve for your roller coaster. So obviously I made up this picture, a side view of a roller coaster with some made up data that's different than your data, but it should be the same basic idea and certainly the same requirements for calculations. So you can pause the tape and copy down this side view of the roller coaster and all the data. You're probably starting right away, and just some things. I'm saying that it's a gravity-driven roller coaster, right? So gravity is the only source of energy. So this roller coaster will be held up here at position 1, released, let go, falls on a fairly not too steep a fall to start, then a big steep fall. Position 2 is what I would guess would be the fastest point on this particular roller coaster. Then it goes through a loop. I said position 3 was the top of the loop. You can pick whatever positions you want, like when you're choosing points, and you would have already done that yesterday. If you're a two or three person group, you only have to include 3 points on your coaster. Everyone kind of needs to do the fastest point on your coaster, and you have to do the beginning and you have to do the end. If you're a 4-person group, then you need one other point. So in this case, that would be the point 3 here. Okay, so every group here has to do full set of calculations on this point, and by that point I mean an instantaneous point of time, right? And thinking about things you have to know about that point, you'll have to be able to figure out the instantaneous speed. You can't measure that. There's no timer involved. We're using conservation of energy for each location to find the speed. Okay, and we're going to calculate gravitational potential energy, we're going to calculate friction, thermal energy, kinetic energy, all those things. Okay, and just this is all the data you need to do it. So things that you'll have to do is know, like for example, I said, okay, this steep drop, I'm assuming there's no friction there. I didn't even count the pieces. But you should know up to every single point on your coaster how many pieces there are. So in this case, I know between 1 and 2, there's more than 10 pieces, but I'm only counting 10 of them because I'm saying 10 of them is where it's kind of flat and there'll be friction. Okay? Between points 2 and 3, there's another 12 pieces, and between points 3 and 4, there's another 18. Okay, so that's the sort of data you need to know, and the height of each off the floor. That's how I chose to do it. It's not the way you have to do it, but that's the data that I asked you to collect. So I think it's it's straightforward for everybody. Okay. And at position 4, don't forget your last point, it needs to be at a stop. So it starts at a speed of 0 and it ends at a speed of 0. And your coaster might get to this point and roll back. That's okay. Point 4 is where it stops before it rolls back. Okay, and obviously point 2 and point 3 in this case are stationary. So if you need more time to copy that down, go ahead, and I'm going to show you the next thing I want you to copy down that before we do any calculations. And that's this table right here. This is by the end of this by the end of this video, we're going to have calculated, we're going to have numbers in each of these sort of in our bingo card. Basically, we're going to fill up our bingo card with ET means the total energy at that point. Remembering that total energy is conserved over the course of the roller coaster. Gravitational energy, kinetic energy, thermal energy, and the speed at each point on all 4 points. And again, I'll remind you that if you're a 3-person group, you're not going to do point 3. Okay? So you might say, like all the calculations, what I want to see in your report is say FERD is doing point 1, and it's the easiest point, by the way. FERD, and I want to be able to see that when I look at your report, that it's FERD's handwriting who did all the calculations for point 1. And maybe DREF does point 2, and FERDET does point 3. Actually, let's do FERDET's point 4, because we're going to call in the big guns. We're going to say Gandalf. If you're a 4-person group, Gandalf is going to come in and do point 3. Point 3 is probably the hardest anyway. Everything besides point 1 is pretty hard. Okay, but I'm going to show you how to do all the calculations to fill in this table. I put here at the top maybe the guiding equation that the total energy in the coaster at any given point is the sum of all the types of energies. So you got gravitational, kinetic, and thermal. Those are the 3 types that could exist at any one point. and the total energy is the sum of those, and that we end up using that mostly so that we can solve for kinetic energies. Okay, and then we're going to find the speed. So again, pause it if you need to, but I'm going to move on. Where I want to write down a couple equations. You might want to write down these equations that we're going to be using. Okay, so again, pause it so you can write down those equations for gravitational energy, thermal energy, friction, if you know thermal energy, and speed at any given point. Okay, so these are equations that we can apply to any point on the coaster. There is one big assumption we make in the roller coaster, and that's that where there is, sometimes we assume no friction, like the steep drops, but if we're assuming there's friction, we're assuming it's always the same, which isn't true, but it's an assumption we can make to make the numbers more reasonable. Okay. Okay. So let's start the calculations. Again, if you've needed to pause this or move back at any point. So I'm going to start basically doing calculations for point number 1 here. I'm going to show you, I've already done them, but I'm going to show you and explain all the calculations that I've done for each point on the coaster, and we'll fill out our bingo card. So here's point 1. The information we know for point 1 I have right here. Okay, so this is the stuff that you should know going in. You should know that, well, first of all, the mass of the cart, and I chose 1 kilogram. Yours is what, 17 grams or something like that? So yours isn't a nice number like this, but I just chose 1 kilogram to make it easier for myself because I can. And I'm saying that initial height, the drop height is 5, like from the ground is 5 meters. And like I said, and this will apply for everybody, that your starting speed will be 0. You're not giving it a push or anything like that. It's starting at rest because it's a gravity-driven coaster. So the calculations we can start doing, one you can do every time, as long as you know the height, you can always find gravitational potential energy. Okay, and so that's MGH, so that's easy to do, and you, at least now you know the starting gravitational potential energy. So I'm going to go start filling in my bingo card, because actually this little bit of information I can fill in, that's all you have to do for point 1. I'll show you why. Go back to our bingo card. We know then 49 is EG, but we also knew from the very beginning that we knew that the speed was 0 when we started. Some other things then, because kinetic energy is the energy of motion. If there's no speed, there's no kinetic energy. So I can throw in a 0 for that point too. Okay, so this is Ferd's set of data. Ferd here, who's doing point number 1, we know the, I didn't write down units, but these are all these energies are in joules. So we know gravitational is 49, kinetic is 0 because there's no speed. We know you can't lose energy to friction before you move, so thermal energy's got to be 0. So we'll put that in there. And so now to find my ET, well, it's 49 plus 0 plus 0, right? Using this equation, 49 plus 0 plus 0. So my total energy, and that totally makes sense because it's a gravity-driven coaster. That's what we're saying. Gravity is the entire source of energy. So gravitational potential energy is the total energy for the start of the coaster. And then as the coaster progresses, some of that gravitational becomes speed and becomes friction. Now, while we've got our bingo card up, I'm going to fill in a few more things because the law of conservation of energy tells me that energy cannot be created or destroyed. That means that it's got to have the same total energy the whole time. So 49 is going to be our magic number. It's always going to be the same for the total amount of energy. Okay, energy is not created or destroyed. Total energy stays at 49 the whole time. Okay, what else do I know? But before I bother doing anything else, I'm going to start thinking, no, I guess we're done there. So we know we've got sort of like, I guess we got a couple bingos here. Okay, so again, if anytime you need to pause this video, please do, but I'm going to move back to the calculation, or back to the diagram, I think, to start. So we've sort of solved everything for point 1. We want to move on to one of the other points. I think usually what I do then, pretty much you have to, is you have to kind of do it's like not, you can't all work together. Like, you know, if Ferd's doing point 1, Ferd's got to go first. And then Ferd can twiddle his thumbs, while I think it was Ferdette has to do point 4. So we're going to move on to point 4. Because point 4, you have to do second because that allows you to calculate the friction force. So let's jump down. We know the height at 0.4, and the other thing we know about 0.4. Now what's important for 0.4 isn't the amount of track between 3 and 4. It's the total amount of track up to that point that has friction. So that's going to be the 10 plus 12 plus 18. But let's just see. Let's go on to point number 4 here. Okay. So the givens for point number 4, we know the total energy. We know the height. We know it has a speed of 0. That's kind of the definition of our endpoint. So that means the kinetic energy is 0. So that tells us we know a bunch of stuff already. The other thing that I was hinting at when I was looking at the diagram above is that the E thermal that matters for 0.4 is the thermal energy that's been lost to the system due to friction since the very beginning. Okay, so it's based on the 49 joules that started. So since the very beginning of the coaster, how much energy was lost? Okay, and so that means that we need the piece of information that we need then is how much distance was, because E thermal equals friction times distance. So we know the distance. We know that there's 40 pieces, and I just gave a nice easy number of 1 meter per piece. Here's about 30 centimeters or something, but again, you can do all the hard work. I'm just going to use a meter. So in my example, I've got 40 meters of track where friction counts. Okay, and then there's another so many meters of track, that's the drop that I don't care about for friction. So that's sort of the givens. That's the stuff I know going into 0.4. And I need to fill in my bingo card. The other piece you need to know about 0.4 is we're going to use 0.4 to find the average frictional force for the entire coaster. So we'll start with EG. So every time you do a point, the easiest thing to start with is solving for the gravitational energy, because it's just mgh. Okay, so that's easy. And then you can remember this equation, that the total energy is just the sum of all the different types. We know that in this case that EK is 0. So that means 49 is our total. There's our EG. There's the 0 for EK. That's going to let us solve for E thermal. So we can figure out that over the course of our coaster, of our 49 joules that went in, 39 joules ends up being lost to friction. And if you think about it, it makes sense. Most of the energy, there's a little bit of gravitational at the end, that little roll up the hill at the end. There's a little bit of gravity, but mostly it's all lost to friction by that point. That's why it stops, right? So of our 49 that went in, 39.2 have become friction, or thermal energy. And then from that, though, we can solve for, using that assumption, we can solve for the frictional force. So again, we're saying where we don't neglect friction, we're going to say it's the same frictional force the whole time. And we can find that frictional force using this formula, which you wrote down earlier. E thermal divided by the distance is equal to frictional force. So we're saying that for our coaster, we have an average frictional force of 0.98 newtons the whole time, besides where we say it's 0. I know it's confusing, by the way, if that's what you're thinking. That's real life, right? Real situations are never easy, right? That's why this is a great project, besides that you kind of get to make something. But anyways, let's go back to our bingo card and start filling stuff in, okay? So for 0.4 down here, we figured out the gravitational force, gravitational energy, was 9.8, right? And E thermal was 39.2. And the speed was 0. And the kinetic energy was 0. Okay. So we only have 2 more rows to figure out on our bingo card. They're actually the 2 hardest. And we've also figured out that Fk equals, don't write that down until I move it, Fk is equal to 0.98. Okay? So that Fk will apply for the other 2 points. We'll have to use that Fk. That's why 0.4 has to go before the other points, because you need that friction force. Okay, so again, pause it if you need to, but let's move on to point number, I think point 2 was the next one I did. Just look at point 2 in the picture. So point 2 in this case is down here. So point 2 has a height of 0.5. We've lost a little bit of energy due to friction because of this sort of flat area. We're going to neglect that length there, so it doesn't even it's not taken into account at all. So point number 2. So here's the givens on this side here. Here's my givens. I know the height. I know the total energy is 49. This doesn't change, right? My distance where there's friction, so that D in this case is always where there's friction, is 10 meters, and Fk is 0.98. I don't know the kinetic. It's definitely moving. It's definitely moving. So there's kinetic energy and speed, but I don't know what they are yet. But something I can do right away is solve for gravitational. Remember I told you the first thing you can start with. So it's 4.9 joules, same equation. And then now we can use the E thermal equation, that it's friction times distance where there's friction, to find out the amount of energy lost due to friction up to 0.2, right? So that delta D is up between the start of the coaster and where that point is, 0.2. How much distance is there where we're counting friction? And the answer is 10 meters. So that gives us our 9.8. Then we can find Ek by saying total energy, right, is the sum of all the different types. And we know the total, we know the gravitational, we know the thermal, and Ek is the only thing we don't know. So we can solve for it. Okay? So you can solve for Ek, and I'm sorry, I just want to keep going so the video is not too long, even though I know I'm probably going too fast. So please stop to write down. But we can solve for Ek, and then remember that to find speed, it's just the square root of 2 times Ek over m. So I think my page got cut off, but that leaves us with 8.3 meters per second. Okay, so now let's go back to our bingo card. And for point 2 then, we said it was 4.9 was the Eg. E thermal was 9.8. Pretty important number in physics. And Ek, I can't remember. What was it? What are you, Ek? And point number 2, Ek was 34.3. And our speed was 8.3. All right, one more row to go. So Gandalf's set of calculations are actually the exact same. It's a repeat of what we did with Druff, just different numbers. Okay, but your goal by you hand in your report will be to have a table like this all filled in. And remember that if you're a two or three person group, you can skip Gandalf's line. But we're going to do Gandalf's anyway for funsies. So let's look back at our coaster. So we're looking at, in this case, the top of the loop. It's just another point. So the points you have to do is start and fastest point, and then some other point. So I just chose the top of the loop. So we know that up until point 3, we've got 10 plus 12 pieces of track, which in my case works out to 22 meters. We know the height's 1.5. Okay, so position 3. So again, over on the left here, these are all the givens. Okay, this is the stuff we know going in. Again, the force of friction is 0.98, total energy is 49, that doesn't change, and we have 22 and 1.5 for our length of track where there's friction and the height of 1.5. So again, start by calculating Eg. So if you're getting started on your calculations, just do Eg. It's a safe one. We can solve for E thermal because we know our friction and we know our length of track up to that point. And same process as point number 2 to find for Ek of 12.74. Again, I know I'm going fast. Just pause it, okay? 12.74 because we know ET is 49, Eg is 14.7, E thermal is 21.56. So that leaves just what does Ek have to be, right? Just so that we can solve for that. Once you know Ek, you find the speed using square root of 2 Ek over m, and that leaves us with 5 meters per second, which makes sense. Makes sense it's going a little slower there than it is at the fastest point, right? So let's fill in our bingo card, and that'll be it. What have we got? Eg. Oh, it was 9.8, right? 1 meter high. No, 14.7. See, no one can correct me. I have to correct myself. 21.56 was the kinetic, if I remember correctly. And the thermal, can't remember. What rate of thermal? Oh, that was thermal in 12.74. Thermal, sorry, and 12.74 for the kinetic. And our speed was 5 meters per second. Okay, bingo, we did it. Okay, so I'm going to put this video under the Schoology. So if you get stuck while you're doing your calculations, because between today and tomorrow, I'd like you to have your calculations and your report done. Make sure you follow this description of all the things you need to do for the report. So you can get a picture of yourself in there too with your coaster. And yeah, that's it. I'll see you on Thursday.